So, hi guys, my name's Siddhant.
My name's Matt.
And along with Sammy, who sat right over there, we're working with Professor Sean Matt and Dr. Victor C., aka Spinny Chair Guy, and we're working on rotation, magnetic activity, and the winds of sun-like stars.
All right, just a quick overview. Initially, we're going to be going over the motivation of our research, so the whole reason why we think that this is worth looking into. And then we're going to be looking at describing to you the introduction. So there's going to be two main concepts we're going to be talking about is stellar rotation and magnetic fields. And then we're going to lead on to talking about stellar winds and how they link back to the rotation and the magnetic fields.
Then we're going to be talking about rotation rate evolution, so how the spin of a star evolves over time. After that, we'll be talking about what the crux of our project is, since that's an investigation that's been done, but we want to investigate something called open flux, and that's a relatively new area of research. It's quite exciting. And then finally, we'll be telling you the aims of our Master's project, what we're going to do, and we'll be looking ahead. So, to kick it off, the motivation for our project.
Right. So as we're fully aware that the Earth is being constantly bombarded by cosmic radiation and solar radiation from the sun and different sources in deep space. But we're mainly protected by the Earth's magnetosphere, its magnetic field. But there's still an interaction which happens with the environment and between the radiation and the magnetosphere. We see this in terms of the aurora borealis and the northern lights. And sometimes when we get solar storms which are large enough, you can actually get shut down of some power stations. So even though we have the magnetosphere to protect us, there's still an interaction with the environment which does affect it. So it's important to understand what the space weather is like.
We basically want to understand the magnetic field of stars based on their rotation evolution. So we can look at the sun and we can sort of directly observe the magnetic field of that and see how that impacts planets like Earth. And it can also give us clues about exoplanet habitability. So with the other exoplanet talks, we saw about how we could detect them, and I think Jayesh mentioned the habitable zone. But even a planet there, let's say the star that it's orbiting has a really strong magnetic field, or it's really magnetically active, it might be possible that that planet isn't habitable purely based on the radiation reasons. An example in our solar system is Mars. It has effectively no magnetosphere, and it's a barren wasteland, even though it's just on the cusp of that habitable zone. So this could be another way of sort of weeding out potential candidates.
Right, so just to start you off with an introduction of some very core concepts that we require in order to understand our Master project is, long story short, stars spin. Now, as discussed in an earlier talk, stars form from cloud collapse due to gravity. Now, these clouds orbit a common center of mass. And this common center of mass, tends to have a net rotation. This can be due to gravitational shear effects from other orbiting bodies, because as we know from earlier, stars form in multiple groups from the same cloud. Now, this rotation rate that the cloud has, the rotation must be sustained when the star collapses. Angular momentum must be conserved. So, it's the gas cloud's initial rotation is what gives the final star its rotation rate, i.e. its spin. You can think of a star spinning as not too alien from what we're used to. For example, the Earth rotates on its axis 24 hours as we know it. You can think of it similar to other stars. So the Sun, for example, has an average rotation rate of 26 days, and a rotation period of 26 days. So it takes 26 days to rotate on its axis on average.
We want to investigate stars on something called the main sequence. That's basically just a series of types to which most stars belong. The Sun is on this sequence, and it's the longest and most stable period of a star's lifetime. So why did we choose this? Well, our project is on Sun-like stars, so it's important to choose things that are close to our Sun, and that happens to be a lot of the stars on the main sequence. Our aim is to investigate how the rotation rate of stars like our Sun evolve over time. And as I mentioned before, the Sun is important because it's the only star that we can actually physically observe. We can send spacecraft there and actually take measurements. Everywhere else, we have to infer from other physical parameters.
Right, so the second concept, since we talked about the fact that stars spin, is magnetic fields. Now, if you combine, so let's just start off with, a star is a big ball of plasma, and the plasma contains charged particles. Now, if you combine the charged particles with the rapid rotation of the star, as we've just discussed, you end up getting current loops. And as we know fundamentally, when you have a change in current, when you have some current loops producing, they produce a magnetic field themselves. So since a star is a big ball of plasma, which rotates rapidly, that produces its own magnetic field, similar to that of a bar magnet, you could say. And this is what provides the energy for the magnetic field. It comes from the actual rotation of the plasma itself. And this we can observe directly with the sun because it's so close to us, but with other stars, it's quite hard to measure the magnetic field directly. So we have to use a lot of indirect methods called Zeeman Doppler imaging, but we won't go into that much detail in this talk.
And we know that magnetic fields deflect charged particles. In our case, that's plasma. We can see it here on Earth in laboratories. And these same magnetic fields of stars actually deflect the plasma of the star. And it leads to them being expelled. And along the field lines, along the magnetic field lines, this is a phenomenon known as stellar wind. And it's very, very important for, it's very, very important for our investigation.
Right, so this is a simulation from the visualization student from NASA, and what this is modeling is stellar radiation, also stellar winds coming from the sun, as you can see here. Now, stellar winds are basically, you just have to care about a continuous flow of charged particles, and we can consider them background because this is a continuous steady state flow. And we can see this interact with the Earth's magnetosphere.
Yeah, so here, maybe it's better if I point there. Here you can see the Earth, that's the sun. You can see these particles actually being deflected because of the Earth's magnetic field. That's all the solar radiation, and we're protected because of this field. Let's say if we took a solar system, like an extrasolar system, and if we said this star had a very high magnetic field, you'd see much more incident radiation. And if this planet didn't have as strong a magnetosphere as the Earth, or it couldn't cope with that sort of solar radiation, it would have probably very detrimental effects on the environment. So that's just bringing it back to the sort of exoplanet habitability argument.
Right, so we talked about rapid rotation of stars, or stars rotating themselves, the magnetic fields, and we defined what stellar winds. Now we're trying to bring them all together because stellar winds are due to the magnetic field, which is due to the rotation of it. And now we're going to talk about how they affect rotation rate evolution, so how the star's spin evolves through time. Now, as we discussed, that stellar winds are just they're just continuous flow of charged particles. Now, these charged particles we know interact with electric and magnetic fields. They interact with the magnetic field of the star, and this produces a force on them. Now, since the star is also spinning, this force goes against the rotation of the star, which means it's acting against the rotation of it.
So basically, you can almost consider it like a lever arm that's coming out of the star, like a torque wrench, and it pushes against the rotation of the star and acts to slow it down over time. So gradually, over time, you see stars that could have been rotating very quickly eventually slow down over millions or billions of years.
Right, so this is some actual data. This is what we can observe, and this is what we end up using to build our model. So this is a graph from Gallium-Bouvier 2013. So just to describe some of the units for you, this is in rotation rate in terms of solar units, so just multiples of how fast the sun rotates, versus age in millions of years. Now, just explain some of the data points and what you might be wondering why they're in lines. So we observe this rotation period data from clusters. Now, what we assume is that open clusters, all the stars have started from the same stellar nursery, so they're at the same age. So hence why they're a straight line in the time region. So we measure a bunch of data from each cluster, and we can see them like snapshots at different evolution in time. These aren't the same stars which are evolving, but by looking at different ages, we can see how a star should evolve, starting as a fast rotator going down.
Yeah, just to add to that, from Aaron's presentation, you could see that it sort of formed many stars almost at the same time interval, or so close together that it doesn't matter the interval of which they're separate. So that's why we just consider all these stars in a cluster to just be of the same age. Now, to break it down, this is the area we'll be considering. I spoke about the main sequence, and this is what it encompasses. It is, because it's in a logarithmic scale, this is the main part of a star's lifetime. This is very small in comparison to this time frame. So you can see fast rotators and slow rotators here, and you can almost see this trend of it going down over time. And in fact, they seem to converge to this line. It's not that easy to tell, but they do seem to converge to this line known as the Skumanich relation. And again, our sun is on this line, so it's important to, again, relate things back to something we understand more, which is the sun. And you can see that even the fast rotators and the slow rotators do seem to converge to this trend.
And this is behavior we'd like to model. So now we're going to go on to the crux of our project, which is stellar open flux. So basically, the magnet, just think of a bar magnet, which is something that we all have experience with. A bar magnet has got a north and south pole. So if you threw in a bunch of iron filings where a magnet was, you'd see the magnetic field lines go from the north pole down to the south pole. pretty much the star is just like that. And we consider that the field lines go out from the star and connect back into it. However, it's so large that we want them a few of these lines are direct plasma. They flow away.
So basically a few of these lines, they just direct plasma far enough away that we don't have to consider them to be open. We all know that you can't just have a North Pole or a South Pole. There's always a North and a South Pole. You can't just have a magnetic monopole, as it's known. But for the purposes of our investigation, we do kind of consider that. We are guilty of that. But they do connect back up eventually. It's so far away, we can consider them to be open. And this basically saves us computational power. We don't have to sort of render these as connecting back up at infinity. We can just assume them to be open at some distance from the star. And we actually believe that stellar open flux is the main contributor to rotation rate evolution. So experiments and investigations until now have only really considered the total magnetic field of the star. And that basically completely ignores what the geometry of the magnetic field is. Stellar open flux doesn't. So not only is it less computationally expensive, it's probably more accurate. This is a small diagram that shows the closed field lines here, which we assume don't contribute to the slowing down, and the open field lines. So if you kind of imagine the wrench, then you can see that the open field lines are the things that would be pushing against other matter to slow it down.
Right, so now we're just going to talk about our aims and looking ahead. This is where we come into, because this field has been around for 50-odd years, and this is what everyone's been trying to do up until now. This is where we come in to talk about our open flux and what we're going to be trying to do over on our master's project. So ideally, we'd like to model the evolution of stellar rotation rate for solar-like stars, and we would like to model the magnetic activity within solar-like stars, so specifically look at the geometry where we can estimate the open flux.
We also want to investigate the effect of stellar winds and, as I mentioned, stellar open flux on the evolution of rotation rate, since we believe that is the main point that needs investigating. And fun picture from Professor Sean Matt. Here is a star. You can see the closed field lines here, and all of these are open field lines. And you may be wondering why they're not just like flat and straight out. It's because the star is modeled as spinning, so you see these field lines spinning around as well. So, thanks for listening, guys. Any questions?